Hello everyone, welcome to the course on machine learning using Python programming. In today's lecture, we will see some metrics or measures of similarity and dissimilarity, and these metrics are useful in the sense in many of the machine learning algorithms or machine learning models. We use these similarity metrics or dissimilarity metrics, and in the second part of this lecture we will see cross validation, that is again an important topic in machine learning. So, let us start measures of similarity and dissimilarity. So, first we will see all the similarity measures and then dissimilarity measures. So, generally as we have seen, there are different types of features in our data set. So, if your features are numerical features or continuous features, in that case we have these similarity measures: Euclidean distance, Manhattan distance, Minkowski distance, cosine distance, Jaccard similarity distance, and Pearson correlation coefficient. And if features are categorical features, in that case we have Hamming distance. So, these are the metrics that can be used to find similarity between two instances or similarity between any of the instances in our data set. So, let us see these metrics one by one. First is Euclidean distance. So, we know this is a very famous metric for finding distance between two instances. So, this is the same is written here: P1 minus Q1 square plus P2 minus Q2 square. So, this is the Euclidean distance metric, where P1 and P2, we can say that there are two instances. One instance is P. So, there are two features. For instance P, the features values are P1 and P2, and for instance Q, its feature values are Q1 and Q2. So, we find Euclidean distance between these two instances by this formula, that is P1 minus Q1 square plus P2 minus Q2 square, and then we take the square root of this. So, if we have n number of features, so n number of terms will be added here. So, this is the formula of Euclidean distance. Now, let us see, there is another distance metric, that is Manhattan distance. So, if we want to find out similarity between two instances, then we can use this Manhattan distance also. So, in this Manhattan distance, we say it is a sum of absolute differences between these data points across all the dimensions. So, you see here it is absolute difference between these data points across all the dimensions. So, this is the first dimension, this is the second dimension. So, mod of P1 minus Q1 plus mod of P2 minus Q2, if they are n dimensional data set, in that case here we will have n terms regarding that. So, this is the Manhattan distance. So, you see difference between Euclidean and Manhattan distance. Here we are taking square of this and then finally square root of this. Here we are taking absolute difference and we are not taking a square and then finally square root. So, this is the main difference. Then we will see Minkowski distance. So, this we will see this is basically generalized form of Euclidean as well as Manhattan distance. You see its formula is this. So, if we take the value of P as 2, in that case it will be looking like this. mod of pi minus qi to the power 2. So, it will be in that case your Euclidean distance it's and under root p is there. So, you will have this square root in that case. So, this is this will now lead to the Euclidean distance if we take value of p as 2. So, in general here we are taking in place of 2 we are taking p. So, we can have any value of this p. So, that is why it is generalized form of Euclidean distance. And then if we take value of p as 1, you see if p as 1, in that case it will become summation I is equal to 1 to n mod of pi minus qi and then 1 upon p. So, that is 1 upon 1. So, it is 1 only. So, this is nothing but Manhattan distance. So, that is why it is generalized form of Euclidean as well as Manhattan distance. If you take the value of p as 2, it is equivalent to Euclidean distance. If you take p as 1, it is equivalent to Manhattan distance, but we can take any value of p and based on that we will get the distance. The next similarity measure is cosine similarity. So, in cosine similarity, it measures cosine of angles between two vectors. So, here we know vectors are nothing but different your instances in the data set. So, one vector is corresponding to first instance suppose and another vector is corresponding to second instance, and this we are denoting as x and this instance we are denoting as y. So, here in case of cosine similarity, as we have done in Euclidean distance or Manhattan distance or in previous distances that we have taken, there we are, when we are finding distance, we are taking absolute value or basically difference of these different values in different features or in different features or different variables corresponding to different dimensions. While in case of cosine similarity, we are not finding distance between corresponding features. Here we are considering these as a vector and we are taking distance as a angle between these two vectors. So, if x is suppose this vector and y is this vector, so this cosine similarity is basically showing you what is the angle between these two vectors. If both of these two vectors angle is same, then this cosine similarity will be 0. So, here the formula is x into y upon mod of x mod of y, and its range is from 0 to 1, and if we take some variation it will be from -1 to 1. So, generally cosine similarity we use when we talk about text analysis or we do document similarity or recommendation system, and in many other cases you may use cosine similarity. So, it will depend on the application, it will depend on your data set. You will need to analyze whether you should use Euclidean distance or Manhattan distance or cosine similarity and so on. Depending on the application, you can find out some metric may be more useful while others may not represent the actual distance that is there between two instances. So, next similarity metric is Jacquard similarity. So, this basically measures similarity between two sets by comparing their intersection to their union, and that is why its formula is mod of intersection of A and B upon mod of union of A and B. So, if your data set is like you are working on some set based data or means you can take some binary attributes or your categorical variables are there. In that case, you can use this Jaccard similarity metric. Then Pearson correlation coefficient, and it is also very famous coefficient for finding similarity between two instances. So, we can say that it measures linear correlation between two variables, or in general if there are more than one variables or your data set is n dimensional data set, in that case you can find out Pearson correlation coefficient between these two instances. So, this is this Pearson correlation coefficient is generally denoted as R, and it is summation of xi minus x bar. So, where x bar is the mean of all xi's and yi minus y bar is mean of yi upon square root of summation of xi minus x bar square summation yi minus y bar square. So, when we will calculate it, it will always come between -1 and 1. So, it measures relationship in case of regression analysis when its value is 1. In that case, we say that there is a means when we can say that the relationship between x and y is high. When we will increase x, y will also increase, and when the value of Pearson correlation coefficient is -1, in that case again these are two highly correlated, but in that case if x will increase, your y will decrease. So, this let us see another similarity metric. So, that is Hamming distance. So, Hamming distance can also be used to find distance or similarity between two instances. So, Hamming distance measures the similarity between two strings of the same length. So, here we can use Hamming distance in the case when you have instances, and those instances of course must have the length same. So, generally in case of machine learning, when we talk about n dimensional data set, in that case each and every instance will have n features values, and that is why this condition will be satisfied. But here we generally calculate Hamming distance when your features are categorical features, because that as per the definition it is number of positions at which the corresponding characters are different. So, we can compare these two directly when this feature is categorical feature, and suppose we are having here some value a, here some value a, then the number of positions. So, in this case if value is b, here e, so this is another feature. So, we will count the number of positions where these are different. So, that is the Hamming distance. So, we can say that it is useful in case of binary data or text data like DNA sequences. Now, we will see some dissimilarity measures. So, in case of dissimilarity, we have already seen Euclidean distance and Manhattan distance. So, both of these two metrics we can use as a similarity or distance metric also, dissimilarity. So, if this Euclidean distance value is high, it means these two instances are dissimilar to each other, and if its value is low, in that case there are chance you can say that these two instances are similar to each other. So, now we will see few more dissimilarity measures, that is Mahalanobis distance, Canberra distance, Chebyshev distance, that is also called as maximum distance, and edit distance, that is Levenshtein distance. So, let us see these distances one by one, and Euclidean distance and Manhattan distance we have already seen. So, these two distances can be used as a similarity or dissimilarity matrix. So, depending on the context we can interpret these, but the metric is same. Now, let us see what is this Mahalanobis distance. So, basically generally when we calculate or use Euclidean distance, in that case each and every feature So, if suppose these are two instances, instance I1 and instance number 2, these are different feature values. So, these are your independent variables or predictors. So, when we want to calculate distance between these two instances, in that case your Euclidean distance assumes that all these features are independent, but if this is not the case, in that case your Euclidean distance will not give you the actual distance measure or actual similarity or dissimilarity between these. So, in that case, to handle this case when your features are independent, this distance metric is proposed. So, here your distance takes into account this covariance between these dimensions. So, if this covariance is high, so in that case your Euclidean distance may not give you the correct result, but Mahalanobis distance will give you the correct value, and it is defined like this. This is square root of x minus y transpose S inverse x minus y. So, where S is nothing but covariance matrix and x and y, these are two different instances. So, generally this distance metric we use when your data set in your data set your features are correlated with each other, or you can say your dimensions are correlated with each other. Now, we will see the next distance. So, let us see Canberra distance. So, this distance is defined like this. You see it is summation over I from 1 to n, and it is mod of xi minus yi, mod of xi minus mod of yi upon mod of xi plus yi. So, here when your features that are having small values, and if you change or we can say that there are two instances I1 and I2, and there are few features in which values are very small, while in other features these values are not these values are high values. In that case, if there are some changes in these small values, they may be important to us, but in other metrics like Euclidean distance, all these features are treated you can say equally. So, here you see this mod of xi minus mod of yi is divided by mod of xi plus yi. So, you are normalizing it, and because of that you can say that this distance is sensitive to the small changes or small values in different features. So, this is Canberra distance that we can also use, and when we know that there are some features that are having small values, or there are some instances in which values are very small. So, in that case we must use Canberra distance. Then this Chebyshev distance, that is also called as maximum distance. So, in some applications you will see that when there are number of features, feature 1, feature 2, feature 3 and so on, suppose feature m, and these are the two instances I1 and I2. So, there will be values, but we are interested in those distances or those values where this distance is maximum. We are not interested in remaining distances, we are interested in finding what is the maximum distance to any of these features. In that case we should use Chebyshev distance. So, it is defined like this maximum of xi minus yi. So, for the ith feature for which this distance is maximum, it will treat only that distance as a final distance between these two instances, and rest of the features distances will be ignored by this distance. So, we can say that generally these are the use cases of Chebyshev distance. When in chessboard there are movement and we want to find out distance between two movements, or max-min optimization problems. There we are generally interested only in the maximum distance of any two values, and we ignore rest of these. So, and that is why it is also called as maximum distance. The next distance, that is called as edit distance, and it is Levenshtein distance. So, it is generally this distance is used when we have instances like strings, or we can say that if we have instances that we can represent as a string. In that case, this edit distance is defined as minimum number of operations to transform one string to another string. So, in this way you will find out how much distance between these two strings is. If only few operations are needed to transform one string to another string, it means distance between these two are less, otherwise distance will be more. And generally these operations are defined as insertion, deletion or substitution. So, you may insert some element in the previous first string, you may delete some element from the first string, or you may substitute some element with some another element, and then finally that first string can be converted into second string. So, these are the operations. Of course, these operations will depend on the actual application, but generally we have these are the common operations that we apply to transform one string to another string. And its edit distance is used in generally in case of text pre-processing or DNA sequence alignments. So, we have seen lots of similarity and dissimilarity matrix. Now, we must know in which case we should use the which particular similarity or dissimilarity matrix. So, when your features are continuous features or your data is continuous data, then only we can use Euclidean, Manhattan or Minkowski distance. If your features are categorical features, in that case we can use Hamming or Jaccard distance. So, we have already seen if your data is binary data or it is categorical data, then we can use this Jaccard distance. And in case of high dimensional data, when we are not that much interested in the absolute values differences in these instances, in that case we can use cosine similarity. Now, we will see the next topic, that is cross validation, and it is a very important topic in case of machine learning models, because we will see there are lots of advantages of cross validation. So, let us first see what is cross validation technique. So, it is a resampling technique and it is used to evaluate the performance and generalizability of a machine learning model. So, we have already discussed what we mean by generalizability of a machine learning model. So, when you train your machine learning model on the training data set, then whatever performance you are getting, that is only on the training data. Then for the new future data that is not already been seen by the model, so on that new data, whatever will be the performance, that performance or that you can say accuracy, you will say that that accuracy will we can treat as a generalizability of our model, means how much generalizable your model is. So, how much accurate result it is giving on the future data also that has not already been seen by the model. So, your cross validation helps in that also. Then so what is this? Generally means we can say that cross validation, in case of cross validation, we partition the data set into multiple subsets that are called as folds, and then using different folds we do the training, and the remaining fold will be used for the testing. So, basically we can say that if this is a data set, so in case of cross validation, what we do, we divide this data set into equal subsets or folds. So, suppose these are this data set is divided in 5 subsets. So, there are 5 folds. So, what we will do, at each iteration we will train your model with suppose these 4 folds, and we will test it with the remaining fold. So, next time we will train your model with suppose these folds, and we will use this as a testing fold. So, in this way we will see this, this is the idea of cross validation. So, here we can say that your goal is to ensure model performs well on unseen data, because each and every time you are checking the performance on the remaining fold that was not used for the testing for the training purpose. So, for training we used some n minus 1 folds, and we are testing it on the remaining nth fold. So, that is why it ensures you that the model performance is well on the unseen data. So, there are less chances of overfitting or underfitting. So, this is the way. First we split the data into k equal folds. After that, in each iteration k minus 1 folds are used for training, and the remaining 1 fold will be used for the testing, or it is called as or we can say that it will be used as a validation. And finally, we will test our model on the totally new data. So, then this process will be repeated k times. So, in that case you can say you are getting total k folds on which your model will be tested, and it was not trained on those k folds in different iterations, and that is why you may this is giving you the opportunity for making it more generalizable, your model more generalizable. So, then finally, how we will aggregate results, because we trained this k times, we trained the model with k times. So, performance metric, any performance metric that we are calculating, accuracy, precision or equal, this will be averaged across all k iterations. And so, we can assume that when since we are getting the final output by aggregating results of k models, so you will definitely get better results. So, these are the advantages of cross validation. It improves model generalization. We have already seen it. It provides robust performance estimate, because we are taking aggregate when we are giving the final accuracy, we are taking aggregate of k different iterations accuracies, and that is why we can say the result will be more robust and efficient use of data. So, you see your data set, if this is the number of data sets, the number of instances in your data set is 100. So, but in that case, if we use 80% for training and 20% for testing, but here the same data set we are using several times. So, we divide it in different folds. So, using the less number of data, we are using it in efficient way and trying to get your model that is more generalizable. These are different types of cross validation, k cross validation that we just talked about. In that case, your data set will be divided in k folds, and we will do these k iterations. In a stratified k fold cross validation, in this case, in each and every fold, we will ensure that your each fold has a proportional representative of each class. So, generally we have the problem of imbalanced data set. So, in that case, in one data set you may have many instances corresponding to one class, but very few instances corresponding to another class. So, since here the data set is divided in different folds, so the same problem we may have in different folds also. So, that is why we use a stratified k fold cross validation technique, where we try to check and ensure that each and every fold do not have this imbalanced data set problem. And this is also very common cross validation technique, that is leave one out cross validation. So, in this case each data point is used once as a validation test or test set, and the remaining data points are used for the training set. But definitely in this case if your data is very large, and since every time we are using only one as a test data and remaining as a training data, so number of iterations will be very large, and that is why it will be computationally very expensive, and it will provide you unbiased estimate also, because only one data we are using as a test data. But these are the most popular, most common different types of cross validation.
Now we will apply this k-fold cross validation technique, and we will see if logistic regression machine learning model is suitable for this breast cancer data set. I mean, this data set is available in scikit-learn.org, right? So that we have seen, right? So now let us see about this data first. So this data contain data related to the patient with the breast cancer. So if it has basically 569 rows, let me show you that one. So basically it is having a 569 rows of data, and each row has 30 columns. So since this data are having a 30 columns, the data set is considered as a 30 dimensional. The column names are related to the cancer cell. For example, let me show you the column name. So these are the column name which this data is having, like a mean radius, mean texture, mean area, worst perimeter, worst area, worst compactness, and etc. Right? So we can load this data set by calling load underscore breast underscore cancer function of the data set module, right? So the above, this code return this cancer object, which is a bunch object basically, right? So a bunch object store the data in form of key value pair. So when this, if you execute this statement, so we will have the data set downloaded from this scikit-learn.org site. So that we have to download our data set, and this cancer.data refers to the rows of the data set, and this cancer.target refers to the target value, which is either 0 or 1. Here basically 0 indicate the malignant cancer, and this 1 indicate it is a benign cancer. So this benign cancer does not spread, right? We are knowing about it. So benign, this benign cancer does not spread to the other part of the body, hence less dangerous, whereas the malignant cancer is highly harmful and needs serious medical care. So this data.target, this column here basically represent only the value that is either 0 or 1 depending on the type of cancer. So the output is as we have seen, it is a 0 or 1 only. So that means it is a binary classification, right? So for this purpose we can use any classification machine learning model, like we can use the logistic regression, or you can go with the SVM or naive Bayes or decision tree or random forest model. Now, of course, which model is highly suitable for this data set? That depends on the accuracy obtained from k-fold cross validations, right? So now let us understand this k-fold, how this is going to be implemented. So suppose we want to divide the data set into 5 blocks, or you may say 5 folds, and we have to take the 4 block as a trained data set and the other 1 block as a test data set. Then we should take this k is equal to 5, and we have to create an object to k-fold class and specify the n split, right? N split value as a 5, right? This k value we are putting as a 5. Now to apply logistic regression machine learning model, we have to create an object of this logistic regression class with the solver as a solver parameter, and here we have value, the solver parameter value we have given as a leave linear. So basically this leave linear is used generally for binary classification. So there are other solvers as well, like Newton's dash CG, LBFGS, LibLinear, SAG, Saga. So the default value of LBFGS, that is the default value for this, the solver. For a small data set, basically LibLinear is a good choice, right? So that part always we should understand. Whereas we use this SAG or Saga, this one for the faster, these are the faster for the large data set. So for multi-class problem, only we use this Newton CG, SAG and Saga, right? And they are highly suitable if we are having a multi-class classification. Now, so far we have created this KF and model object. Now we have to call this cross underscore well underscore score function to obtain the accuracy scores in each step. And after the model has gone through all this k-fold cross validation, the cross well score function takes the model object and this input x and target y along with this k-fold class object kf, right? So if you see here, the k value was 5, so we have obtained this 5 accuracy score, right? So this k-fold cross validation takes the final accuracy as the average of this value. So now we have to calculate the average mean, right? So that we can calculate that like this way. So logistic regression basically, this logistic regression model gives the accuracy of 95% when applied to this cancer data set, right? Now, same thing we have done and we have applied this decision tree classifier on the same data set to check what accuracy it will give you. So, let us now apply this, this decision tree classifier for the same breast cancer data set. So, in this case also, we are going to be take this k value is equal to 5, right? And we will check the final accuracy after executing this code, and we'll compare both the classifier each other. Logistic regression with the decision tree over the breast cancer data set. So here we are creating a decision tree classifier object with the default values, right? So now we are applying this, this decision tree classifier we have applied. Now see, this is the output of decision tree, how decision tree will give you the output. So this is a decision tree corresponding to this data set, right? So that we will not discuss currently. So only for the understanding, I have plotted it. So if you want to see how decision tree will look like, we have to use this plot underscore tree. We have to import it from the sklearn.tree, right? And then we have to plot it. Now, important part here was the accuracy, right? So now, after applying this k-fold cross validation by calling this cross underscore well underscore score function, the score is coming as like this, corresponding to each k value, right? Now we have to take the average score from all these 5 steps, right? So for the average, we have taken the mean. So this is coming as the outcome. So decision tree classifier basically give you the accuracy of 91% when applied to the cancer data set. Now, what is the conclusion then? So the final conclusion can be discussed now, right? So basically, logistic regression model has given us the accuracy of 95%. And whereas decision tree classifier has given us the accuracy of 91%, right? So the logistic regression model performed well on the breast cancer data set compared to the decision tree classifier. Also, this logistic regression model is a plain linear model. So it does not have a repeated processes internally, right? So that we know, if you recall the algorithm of logistic regression, there is nothing kind of repeated process internally. But if you recall the decision tree, so basically decision tree should test several conditions to take the decision based on this tree, right? At each node, and this test continue to be repeated. So it is a basically iterative iterative model, right? That takes a lot of processor time, right? Processing time. So basically this decision tree and random forest are iterative model that uses more processor time, and hence they produce the result very slowly, right? So that part we should understand. But here in our case the logistic regression can produce better result, and here in our case it is giving us the better accuracy as well. So hence we may say that the logistic regression, it is a final winner in the case of this breast cancer data set. So this type of conclusion is very important for any data scientist or for any student who is doing this modeling.
So, in this lecture we have seen some similarity and dissimilarity matrix, and then we have seen in which particular case we should use which particular similarity or dissimilarity matrix, and then we have seen K cross validation, that is one of the most important concept of machine learning. Thank you.